Hello students, this is Latif sir. Today I am going to discuss about de Broglie on equation and factor affecting conductivity and Kohler's equation, Kohler's law. So first de Broglie on equation, and this equation gives the relationship between molar conductivity, that is lambda m, and molar conductivity at infinite dilution, that is lambda m 0, and value of lambda m 0, that is conductivity at infinitely dilution, is always higher than the conductivity at any particular concentration. And lambda m, how lambda m varies from lambda m 0 or lambda 0 m, that is conductivity, molar conductivity at any particular concentration is equal to conductivity at zero dilution, that is lambda 0 m minus b root c, where c is the concentration of solution. From this equation, it is clear that for strong electrolyte, the conductivity at infinitely dilution is always higher than the conductivity at any particular temperature, a particular concentration. And the equation, the relation between lambda m and lambda m 0 is lambda m is equal to lambda m 0 minus b root c, where b is a constant, and this constant depends upon the nature of solvent and temperature. Next, factor affecting conductivity. There are many factors which affect the conductivity. First, nature of electrolyte. Nature of electrolyte. The strong electrolyte like KNO3, KCl, NOH, these are strong electrolyte, etc., are completely ionized in aqueous solution and have high value of conductivity, molar as well as equivalent conductivity. Okay, because strong electrolytes are completely ionized in aqueous solution, producing a very high number of ions, positively charged and negatively charged ion. The but for the weak electrolytes which are ionized to a lesser extent in aqueous solution. That's why for solution of weak electrolytes which have lower value of conductivity, molar as well as equivalent conductivity. So conductivity depends on the nature of electrolyte. Second, concentration of solution. The concentration of solution of strong electrolyte have significant interionic attraction. The the concentrated solution of strong electrolyte have significant interionic attraction, which reduce the speed of ion and therefore lower the value of lambda m and lambda e. The dilution decreases such interionic attraction, huh, and increase the value of lambda m and lambda e. So on dilution, molar conductivity of a solution increases. The limiting value, conductivity, molar conductivity at zero concentration or at infinite concentration for strong electrolyte can be obtained by extrapolating the graph to the molar conductivity axis. Okay, but for weak electrolyte, in case of weak electrolyte, the degree of ionization increases with dilution, which increases the value of lambda m and lambda e, and the limiting value of lambda m that is conductivity at infinite dilution or zero concentration, cannot be obtained by extrapolating the graph. That is for weak electrolyte, you can for weak electrolyte, the degree of ionization increases with degree of ionization increases with dilution, which increases the value of equivalent conductance and molar conductance, or molar conductivity and equivalent conductivity. The limiting value of molar conductivity, that is lambda 0 m, cannot be obtained by extrapolating the graph. This is for weak electrolyte, and the limiting value lambda m0 for weak electrolyte is obtained by Kohlraasch's law. Next, temperature, effect of temperature. The increase of temperature decreases the interionic attraction. The increase of temperature increases the decrease of interionic attraction and increase the kinetic energy of ions, and thus speed of ions increases, and therefore lambda m and lambda e also increases with increase in temperature. So conductivity increases with temperature. Now Kohlraasch's law of independent migration of ions. According to this law, molar conductivity of an electrolyte, according to Kohlraasch's law of independent migration of ion, this is valid for weak electrolyte, you have to remember. Okay, because the in concentration conductivity at infinite dilution, you cannot measure the, or you cannot measure the value of molar conductivity at infinite dilution for weak electrolyte by extrapolating the graph. Okay, and you can calculate the value of in limiting molar uh, conductivity at infinite dilution by using Kohlraasch's law of independent migration of ions. According to this ion, molar conductivity of an electrolyte at infinite dilution can be expressed as the sum of individual contribution from the individual ion, that is total total conductivity at infinite dilution is contribution from cations and anions produced by ionization of the weak electrolyte. Okay. If the limiting molar conductivity of the cation is denoted by lambda 0 plus, and that of anion is represented as lambda 0 minus, sorry, here it is also written as lambda 0 plus, it okay, the first lambda the molar conductivity of cation is denoted as lambda 0 plus, and that of anion it is lambda 0 minus. You have to correct this one, this lambda 0 plus. For anion you have to write lambda 0 minus. Okay. Then the limiting molar conductivity of electrolyte is lambda 0 m, molar limiting conductivity of the weak electrolyte according to Kohlraasch's law is equal to nu plus into lambda 0 plus and plus nu minus into lambda 0 minus, where nu plus is the number of cation and nu minus is the number of anion produced by the electrolyte. So according to Kohlraasch, main thing is that you can calculate the limiting molar conductivity of weak electrolyte using Kohlraasch's law, and according to this law, total conductivity limiting molar conductivity of an weak electrolyte is equal to the contribution of conductivity from cations and anions, sum of contribution of conductivity of cations and anions. Okay, so lambda 0 m is equal to lambda nu plus lambda 0 plus and nu minus lambda 0 minus, where nu plus and nu minus are the number of cations and anion. Now application of Kohlraasch's law. Kohlraasch's law, first application is determination of molar conductivity of weak electrolyte at infinite dilution. For example, molar conductivity of acetic acid, which is the weak electrolyte, at infinite dilution can be obtained from the knowledge of molar conductivities at infinite dilution of strong electrolyte like HCl, sodium acetate, and sodium chloride as illustrated below. So you have to calculate the limiting molar conductivity of acetic acid, that is lambda 0 m acetic acid CH3COOH, and you can write this lambda 0 m acetic acid as lambda 0 acetate ion plus lambda 0 H plus ion. Again uh, you can express this same equation like this: lambda 0 acetate ion, that is lambda 0 CH3COO minus plus lambda 0 Na plus lambda 0 H plus plus lambda 0 Cl minus minus lambda 0 Na plus and lambda 0 Cl minus. Just cut the same ions, lambda 0 for same ions, that is lambda 0 plus lambda 0 Na plus and minus lambda 0 Na plus and plus lambda 0 Cl minus and minus lambda 0 Cl minus, then you will see that in the equation it only lambda 0 acetate ion and lambda 0 H plus ion present. Okay, so using the value of lambda 0 for strong electrolyte, you can calculate the value of lambda 0 of weak electrolyte like acetic acid. So you can calculate the lambda 0 m for acetic acid by using the value of lambda 0 of sodium acetate, hydrochloric acid and NaCl. You have to write like in this manner. Okay, so lambda 0 m for acetic acid is equal to lambda 0 m for acetate ion plus lambda 0 of m for HCl minus lambda 0 m for NaCl. Okay, second application is determination of degree of dissociation of weak electrolyte. What is degree of dissociation? Degree of dissociation, it is the ratio of molar conductivity at specific concentration at a specific concentration C to the molar conductivity at infinite dilution, and it is denoted by alpha. So degree of dissociation alpha is equal to lambda m lambda cm, where C denotes the conductivity, molar conductivity at a specific concentration C, and lambda 0 m is the conductivity at infinite dilution. And third application of Kohler's law, determination of the dissociation constant, that is K, of weak electrolyte, and the dissociation constant for weak electrolyte is K is equal to C alpha square by 1 minus alpha, where K is the dissociation constant of weak electrolyte and C is the concentration of electrolyte and alpha is degree of ionization.